Okay, good show on the road today. Prairie View, anybody Prairie View?
Mr. Chair.
Just the ghost.
Clay Eastwood.
No, everything just says with that being said, let's pick up where we left off. We've done the classical theory of light, and Max Planck had recalculated and solved the ultraviolet catastrophe, and he did that by calculating the average energy, and he did the average energy by using the sum and the Boltzmann distribution, rather than just taking the result of the equipartition theorem, which comes out of doing an integration. And he thought that it was a mathematical oddity, and he planned to allow the Riemann sums to let the h, the width of his things, go to 0, but when he did that, every time it blew up, and he got the ultraviolet catastrophe back. And so finally, if you just left it finite, it didn't blow up, and he got the right form, and if he chose a particular value for h, he matched the experimental data. And a particular value happens to be called Planck's constant. But that was the reason he did it. Okay, he thought it had no real significance. Now, a couple of things about that. One is, Planck's constant can be written a lot of ways. You can write it the way it's done in high school books, in terms of joules and seconds. So, that's it out. You can write H 6.63 times 10 to the minus 34 joule second. A joule second is a unit of angular momentum. We'll come back to that because it's going to be the fact that that particular unit is very important to Niels Bohr because he's working circular problems with simple forces and they conserve angular momentum. And since every experiment tended to have the same constant in it, this tended to make him think that he should set the angular momentum in units of h. Turned out that's not quite what it needed to be. It needed to be h over 2 pi. But it was proportional h. And that's how he got the idea. He didn't spin it off his head. He was looking at classical mechanics and what are called the actions, where you take something like angular momentum or linear momentum and you integrate it around a path. In this case, the path was a circle. There's where the 2 pi comes from. And since the L was a constant, it comes out of the integral. And so you get 2 pi L. And he put those 2 pi L's equal to various values of h. And then that's how he found his orbits. That's how the Bohr radius atom came about. Besides that fact, first of all, it's extremely small numbers. It's kind of easy to remember because the 663 and there's a 3-4. Unless you're dealing with quantities that are about as small as h, it's like looking for little bitty steps in a huge number. You don't have a good enough microscope, you won't see it. So for instance, the angular momentum of the orbits of the planet are quantized to h bar. The L of the Earth is huge, so you would never see this. So except in the quantum world, although things are discrete and quantized, you don't see these facts because they're so small. The second thing is that there's a lot of things lost here. It turns out that almost every time you run into a problem, you're going to get H and C together. So a much better way to write H is either write it this way, HC, the product, which is 1240 EV nanometers. Much, much more useful thing that you can do a whole lot of problems quicker. I'm going to use it extensively today. It tells you some interesting physics. It says that if you multiply two fundamental constants that drive the universe, they're a product of an energy and a length. If the energy goes up, to keep the same number, it has to go down. So if you can find something in a smaller volume, it's more energetic. This is the reason nuclear energies are so much more powerful than our chemical energies, because the size of the nucleus is so much smaller confined in space to what the atom is. And if you make it even bigger space, the energies get even smaller. And there is this inverse relation between space and energy that is built into these two constants that rule the way the universe works. You don't really see that if you write it like this. Now, the way the book likes to write it, which is okay, is that they like to put C over here like a unit and do that. Okay, fine. But the fact of the matter is most of the time in the equations, you're going to have HC. You'll see that over and over and over and over again. And so I tend to think that HC is 1240 EV nanometers. So when I'm working problems, I'll use HC is 1240 EV nanometers, 1240 keV picometers. So here I've raised the energy by 1,000 and I've shortened the distance. This is going to be useful when we do problems involving Compton, because in Compton X-ray studies, the wavelengths are picometers. Therefore, the energies are going to be 1240 keV, or about 1.2 MeV. So you tend to work in things that are half an MeV, 3/4 of an MeV, and that's because of this number. If you go further, 1240 MeV, and you're in femtometers, also known as Fermis. These are the energy levels of the nucleus. You could go the other way. You could, instead of making the energy bigger, you could make the energy smaller. 1240 milli-electron volts, microns. So you start talking milli-electron volts when you start talking about things on the order of microns and infrared radiation. You start talking about electron volts in chemistry when you're talking about things on the size of an atom. When you talk about things that are smaller, in order of picometers, you're in the X-ray region, in the keV. And when you're in the nucleus, you're in the MeV. Now, if I was to build a machine, and we certainly have done this, that's in GeV, then what would be the next? Anybody know what the next one is?
Yano?
No. Huh?
Yano?
No. It's called the atometer. 10 to the minus 18. Higher in energy represents smaller in space. Why do we build big accelerators? Because we want to probe the smallest dimensions of the universe. How do we know how big to make them? Just a Planck constant tells us all.
Is there a limit on this?
No, not in theory. So as I keep wanting to go higher and higher and higher, is there a limit to engineering applications of how big a machine? Yeah. I mean, either I've got a machine that's going to leave planet Earth and go out as long as I'm going to the moon, or I got to make it move in a circle. If I move in a circle, I got to have a magnet to bend it. If I got to have a magnet to bend it, they're only so strong. If they're only so strong, either I need a really big radius in order to make it make the turn, or I got to get stronger magnets. Now we got these things that are 60 miles across that are trying to bend it. Want to go higher in energy? I'm going to have even bigger magnets. At some point, factors of 10 become hard to get. Now, there are explosions and energy of particles that come from outer space, we don't know where, that are more energetic than an exploding nuclear bomb, called cosmic rays. Whatever the heck creates them in outer space must be one hell of a whoop-bang thing, but we don't really know where they come from. We just know they go through Earth. So that's one way we can get to really high energy. But you don't control them. You don't control how many. It's not like a real nice experiment with the accelerator. All right, so we're going to deal with H. Get to appreciate Planck's constant. It drives the universe, you can see. It's like 5 or 6 constants. If they were different than what they are, the whole universe would not behave the way it is. G, 6.61 10 to minus, you got this 11 Newton meters squared per kilogram squared. The universal gravitation that somehow explains how mass pulls on each other. These constants are fundamental. Another one's the hyperfine constant. So get used to them. We'll come back to that one later. All right. Some things to go back and quickly review before we move on to the photoelectric track. At the time that we're getting to the 1900s, people were convinced, have been conclusively convinced in the 1800s that light was a wave. Prior to that, Newton felt rain and things were corpuscular. They were particles. He was able to build his reflecting telescope based upon this idea. But Thomas Young's interference experiment put that kind of to an end. Everybody's convinced light is in fact a wave. If it's a wave, it must have the properties of a wave. So key properties that would talk about how light would interact, for instance, with a metal. The energy of a wave would be directly proportional to the square of an amplitude. This is true of all waves. So if you double the height of a water wave, you get 4 times the energy hitting the beach. So when you're out in Galveston Beach and you got a 2-foot wave and a hurricane comes in and you suddenly have 20-foot waves, you didn't get 10 times as much energy, you got 100 times as much energy pounding that shore. Okay? In the case of electromagnetism waves, the pointing vector tells us how the power is sent to the area, but the point is that it's, again, electric field, magnetic field. Magnetic and electric field are related to C, so it's the square of the electric field, okay? Square the magnetic field, so it goes to square the amplitude. What this means is that if you increase the brightness of light, say double, then you're going to, if you double the intensity, that is, you raise the electric field by square root of 2, you get twice as much intensity, you get twice as much energy on a metal. So the brightness in classical physics of a light is related to the energy. We'll come back to that because that's not what we find in the photoelectric effect. Another one is the energy of the wave is independent of the wavelength or frequency. So it doesn't matter about how quick the waves are coming in or the space between the waves in the ocean. It depends on how big the waves are. So if you're sitting out there and you want to be able to ride a surfboard, you go to Hawaii because you want tall waves. You don't go to Hawaii because you want the waves to be close together. That may be how long you have to wait till a big wave comes in. But the energy of the wave, which will determine how fast you can go on your surfboard, is determined by the height of the wave. So in light, it's by how bright the wave is, not whether it's red, blue, or green. That's irrelevant. Just how bright. Another point, in a wave, it's not localized in space like a particle. It's spread out. And that means if you're a point electron, let's say, then most of the energy of the light is not hitting you. Now you can try to estimate the size of the electron, and you can do like one of those solid angle calculations we did the other day, and figure out how much of the energy from the whole wave actually hits you and how much energy you're absorbing. And if you're held in a metal, you can determine how long it's going to take before you can soak up enough energy to be able to escape. The light's dim. That may take a long time according to classical calculations. There may not be an electron that's emitted for an hour or more. That's what classical says. And here's the problem. Shine light on a metal plate. If the light is too low in frequency or too long in wavelength, no matter how bright it is, you never get an electron emitted. You can melt it, but you will not get electrons emitted. How can that be? If the energy is given to it, can you not rip it off? If you turn down the intensity of the light, so you make it very dim, so you're not giving it much energy, and it's going to take a long time to emit. If it's sufficiently short wavelength, instantaneously, you get electrons emitted. Not in hours. This does not seem to fit the idea of classical physics. What is true is that if you increase the brightness of the light, you get more electrons off, if any are emitted. But if the wavelength is too long, no matter what, you get none. So there is some connection to the brightness in terms of the number of electrons get off, but not whether you get them off and not with the energy that they come off. So this means there's some sort of a quandary here. So here's the experiment that you guys actually have to do for lab. Although we're going to do it kind of a different way. This is the old-fashioned way of doing it. What you do here is you shine light. The light strikes a metal plate. If the light is short enough in wavelength, you'll have electrons that come off. We put another plate, let's say up here. The electrons come up and hit that plate. That makes that plate negative, this plate positive. So the negatives want to go back to the positives, or if you're an electrical engineer, the positives move to the ammeter, the negatives, all right? Blame it all on Ben Franklin and his choice of which one, fur or rabbits or what you want to call positive. Now, that means this current here that's measured in an ammeter is proportional to those electrons. So it's easy to tell when we shine the light on and either I get no current, or I shine the light on and instantly I start getting current. If I increase the brightness of the light, I get more current, indicating more electrons. What I'd like to do is measure the energy of the electron. And that may seem to be somewhat of a challenge. Well, it's not really, because if you think about an electron like a ball, and you throw the ball up in the air, it's kind of like the electron being thrown up this way. If there was no gravity, the ball would just keep going up. But there is gravity on Earth. So when you throw a ball up, its kinetic energy is converted into potential energy by the force of gravity pulling down. And at some point, when all the kinetic energy is converted to potential, then the ball stops and begins to make its drag back down. We can do the same thing with a battery. We put a grid here with negatively connected to a battery, creating an electric field that opposes the motion of those electrons. Now, in the case of an electric field, you know, the electric field goes like this. That's the direction of the force on a positive charge. The force on a negative charge is in the opposite direction. So these electrons trying to go up are having work done on them by that electrostatic field. And that means they're converting their kinetic energy into potential and they're slowing down. So what you do, you make this variable. These electrons will come off with different energies. The most energetic ones were the ones that were least bound to the metal. You turn this up until the current goes to zero. When the current goes to zero, by measuring that battery times the charge of an electron, you determine the potential energy of the most energetic one. But the potential energy was equal to its kinetic energy when it started, just like the problem of the ball. So by measuring the voltage, I measure the kinetic energy, and that's its only purpose. Now I'm going to assume some things. I'm going to assume that energy is conserved. Why? Because the only force I'm talking about is the electrostatic force, and it's conserved force. So if that's true, kinetic plus potential had to equal the total energy the electron had. And where do you get that energy from? The light. This is basically the idea of the photoelectric effect. It's nothing more than a physics 1 energy problem combined with a physics 2 energy measuring the potential energy for this battery. So you combine two things from freshman physics, do conservation plans, and get the answer. What you're going to get out of it with the E is you're going to look at how that energy depends upon wavelength and frequency. According to classical physics, it doesn't. But what the experiment shows is that it does. Now, before the experiment was ever done, Einstein had already disliked some of Planck's work. Looking at entropy and such, he did not like the way he was treating the oscillators in the box one way and treating the photons, or I should say photons, the wave, in the classical box differently. He decided inside the box, the electromagnetic spectra had to be formed of particles. So his view of waves were different. What he said is, he goes, look, this is not really kind of a wave. What it is, if you want to think about it, is a bunch of particles here. We'll have a discussion about whether we really believe that, but we're going to follow Einstein's logic for a minute. And those photons come in and they hit the electron like a baseball or a softball. Okay? And they don't all have to be the same size. So I can throw you, okay, $300 with three $100 bills. The impact of each bill is pretty good. $100, I could do a lot with that. Or I could throw you $300 by throwing you 3,000 dimes. Here's a dime. Go buy something with it. The dime might not be able to do a dang thing. Unfortunately, this is not a case where you can absorb the dimes and build up. It's an all or nothing thing. So if the dime doesn't do it for you, the dime just gets booped and doesn't get collected. It goes on. So it's a one-time thing. Either the photon's enough, bam, and knocks the electron out, or it's not, in which case it may excite it or whatever, and then it gets re-radiated, and it doesn't do anything. The electron doesn't come free. It doesn't sit there and collect up dimes and try to say. It's kind of like people are today. They don't say. The intensity of the light is the $300. It's the same in both cases. But its effect is not the same. Now, if 10 cents would get you an electron, you could buy 3,000 electrons, okay, with those little bitty dimes. All right? So, if an electron has a certain cost, I might be able to buy more of them. So intensity can impact the number you get, provided it's big enough to buy one. So intensity does get into the play, but it's not the individual part. It's a combination of how much does each one have times how many do you have. Just like calculating your total dollar. It's not just the dime, but it's also the fact you got 3,000 of them that determines $300. It's not the fact that you get three. If they were three $1 bills, it's not the same if they're three $100 bills. So you have to consider both the size of the packet, called the photon, and the number of the photon to calculate the total energy. And that's what classical physics is seeing, the total. It's not seeing the corpuscular part. Now, what we believe today, we believe that light, in essence, travels as this wave, but any time it interacts, it collapses comes apart. So it's both a wave and it's a particle. We have experiments and reasons for that we deal with it. So it's dual. We call it duality of nature. And not only it, but you and electrons are also dual. If you walk through that gap in that door, and that door was small enough a gap, you might actually turn into a wave and diffract and be all over campus simultaneously. Or if you bang into the wall fast enough. It is possible, because waves can go through walls by tunneling, that you might disappear and show up on the other side. It's not very probable, but if you were to beat back and forth fast enough against the wall, say 10 to the 47 times per second, after 2 million years, you might actually pop on the other side. This is how alpha decay happens. This is how transistors work in modern electronic devices. All right? They have this duality. Sometimes experiments show them to be waves. And in other experiments, you see the particle aspect. But you never see both at the same time. You see one or you see the other. Einstein's idea, verified by Millikan, is the formation of the entire field of quantum mechanics. And the reason he won the Nobel Prize for that, not relativity. In everyday life, relativity doesn't impact us nearly as much as what quantum physics does, which drives entire parts of our economy, from light sensors to radiation detective to nuclear medicine. Quantum mechanics reigns supreme on a large scale in the modern world. So, important experiment, that's why we want you to do it. Now let me show you something else. So there's a set of FETs. Let me write that. PHET. They're simulations that you can get out of the University of Colorado. So here's one of these. So, for instance, let me turn off the intensity. So I've got a light with no light photons shining on this metal, and I, of course, have nothing coming off. Turn on the photons, and electrons are going. Let me turn off my battery for a minute. And so there's a certain amount of energy and the photons will come across. And in fact, you can measure the amount of current and go through all the type of experiments. There's your current here, here's your stopping battery here. If I increase the intensity,
what kind of metal does this experiment use?
It's got different stopping potentials. I'm not sure what this one is actually set at.
Sodium.
Is that what it says?
Yeah.
I didn't read it. Where you seeing that at?
Under PHET.
Top where?
Right.
Top right under fetch.
Oh, yeah, target and.
Oh, okay. So that determines how tightly bound the electrons are. And so you give it a certain amount of energy, and then you subtract the energy it takes to get rid, and you have what you have left as kinetic. Now, you can turn up the battery to make the field help them. Now speed or tail up. Whew. Okay. That's cool. But that's not going to stop them. Now let's go the other way. If you go the other way,
So can you deplete that plate of all of its electrons?
well, you can have a discussion about that. So let's talk about, you remember that probability thing we did last time? And you remember excited atoms by heat or whatever get pulled out? You remember how many were in the ground state?
A lot.
Yeah, so
Okay.
no.
Okay.
You're not going to get them all out of the ground state. Now, you see some of these guys get across, and some of them don't. All right? So if we're looking for the stopping potential in a problem, you're looking for the most energetic ones. And I'm not there yet because some of them are still getting across. So I keep turning this up until I stop them all. That looks pretty close. So I can actually play with that and find the stopping potential. What that means is that you have 0.8 volts, and then you got to multiply by E, so that means you got to do this really hard calculation, 0.8 EV. Right? You put the E in there. So that's the kinetic energy that this thing had. If I knew the work function, I'd have 0.8 EV to the work function, I would have the energy of the light. Conservation of energy. Kinetic plus potential is total. You can change the intensity all you want, but you're not going to change making them get across. Now, watch what happens if I change it down here. I'll turn off my battery. Doesn't matter. There's not enough energy to liberate them. And it's color dependent. Okay? Unlike what classical physics says. This thing obeys the laws. It's been programmed to obey the laws of physics. So you could go up and start turning up the wavelength till you find out where they get off. No. Oh, I got some right about in there somewhere, 520 something. I can use that actually to find the work function for this material. Too far to get in. Now, so it's somewhere between, how about,
You might be able to type
turn
in the
this
right
thing up
again.
and sweep them all. Somewhere between 541 and 538. Play with it. Test your calculations, by the way. Your homework better match up with what the thing says. They have lots of different things that you can simulate. Almost anything in physics can be simulated in these things. Let's look at a problem in terms of doing this, and let's talk about Einstein. Einstein's idea. So what Einstein does, Einstein says photons, light, not protons, photons, totally different set of mathematics. Photons come with energy values equal to Planck's constant times nu. Some people prefer not to use nu, to use F for frequency. I don't care, pick your pick. Okay? Depends on which textbook. Nu is used for frequency in some, because they also things also have like pendulums and other stuff going on, and they have frequencies, and you want to make sure which frequency you're talking about. So, H nu or HF. However, if you're working with laser people, I find especially, they do not talk about that. They talk about wavelengths. All right? They talk about the wavelength of their laser. Don't talk about the frequency. Why? Because the wavelength will be like, 520, but the damn frequency is like 10 to the 20 something. All right, it's a huge number. remember that F times lambda is speed, which is c. So if you plug in for F, c over lambda, you get this. What's hc?
1240.
1240.
Very useful. 1240 EV nanometers divided by lambda, you have the energy. Really convenient if you measure lambda in terms of nanometers, not meters. Also convenient if you have energy in EV if you need to solve the other way around. Solve very quickly this formula and solve any problem just like that. You start dealing with SI. Welcome to conversion. Well, you're here for 3 hours and everybody had finished in 20 minutes. That's okay. I won't count it wrong, but you're not going to be getting through the test very quickly. Okay? Now, they did this experiment to test it, and what they found was following. Let me see if I can put all of Einstein's logic in here. Einstein says, hey, the photon gets a certain amount of energy, E, from the light. He says some of that energy is going to go to kinetic, and some of that is going to go to potential, whatever that is. He says, you know, inside the metal, electrons can be bound at different amounts of depth. It's in a well. The guys who are the least tightly bound, this amount of energy, we can either call that, I call it W for work function, or your textbook chooses the symbol phi. It's the easiest electrons to rip out. So let's say that's 2 electron volts. That means you need to give 2 electron volts energy minimum to get them out. Now these guys, if you give them 2 EV, they're going to end up like right here. They're still going to be bound. That won't work for them. So they'll come out, if you like give them 5 EV, if you give this guy 5 EV, he's going to come out with more energy than if this guy's given 5 EV. That's why some of the electrons don't get all the way across and some do. It says, let's talk about the most energetic ones. The most energetic in terms of kinetic when they come out would be the ones least tightly bound. So I'm going to derive the formula for them, not for all these other guys who have different energies. So it says, okay, fine. I'm going to do this. He says, I'm going to come out and he says, I'm going to talk about the max kinetic and the min potential. So if I do that, I'm talking about those held that deep. We said we were going to measure this by E times V stop, using a battery to measure the stopping potential, the voltage in which all of the electrons get stopped, and my current goes to 0. So if I rearrange this equation, I have EV stop is equal to the total energy minus the work function. Then the stopping potential is the total energy divided by the charge on electron minus the work function divided by the E. Now, remember, this work function is going to be like 2 EV. And then you're going to divide by an E, so it's going to become a voltage. For this, Einstein says that I'm supposed to put in HF. Now, everything I've done before had nothing to do with Einstein. Right? So here's where Einstein gets in the game. Everything else was conservation of energy. Einstein says, but E is HF. Fine, if E is HF, let's put that in. What the heck, spot? How about stop? I get H over E times F minus V over E. So according to Einstein, that's the equation that relates the stopping potential to the frequency of the light. And he says, let's plot that. Okay. So there's F. There's V stop. Well, that's like X. That's like Y. This is a constant, M. That's B. So this is a straight line. So I expect to see data points like this. I can draw a straight line. I expect a slope of H over E. So measure the slope, and if I knew the charge of an electron, 1.6 10 to the minus 19 coulombs, which by the way, another famous experiment in the next chapter discusses, then I have a way to measure H. Not by chance, the man who measures E, Millikan, is also the man who measures this and verifies Planck's constant. And this minus V over E. That's the y-intercept. So if I know the E and I measure this, by the way, I'll never see these data points here. So they really don't exist, right? Because that means I would need to actually apply a battery to rip them out of the plate. This battery is trying to retard them. This would say I would need to have the battery turn the other way to rip them out of the plate. So they just don't come out. If no voltage at all is applied, it's enough to stop all electrons right here for this frequency. This frequency is known as the cutoff frequency. So I'm not going to measure these data points. You're just extending the line with a ruler to where it intersects. And if you do that, you can measure the work function of the metal. So I now have a way to determine work functions, or the minimum depth inside a well of a metal if I want to build something with it, like a photodetector, or like a filament for emitting electrons in an electron gun inside a television tube. All of that comes out of here. So it has a practical application. It has a revolutionary physics idea. And that is, energy was related to frequency and the world was quantized. Okay, now, hopefully you're going to get me my Planck's constant out of your experiments. Right? You have a series of different lines you have to measure. You have to measure stopping potential. You have to look at them as a function of intensity. You have to look at them as a function of wavelength. That's basically what your little lab is for this week. Let's do a problem. All right, so you got a problem. Look what drives everybody, what's on your thing. So a physicist is performing a photoelectric experiment using a metal with a work function of 3.9 electron volts. Light of a single wavelength falls on the metal. And the stopping potential for this light is then measured to be 0.1 volts. So in other words, at 0.1 volts, he can stop even the most energetic electron from making it over to his collector and measuring current. Calculate the wavelength of the light falling on metal. Okay, so E is equal to E times V stop plus V. Conservation of energy. And E is HC over lambda. So the first thing I would do is I'd calculate the energy of the wavelength for the light. HC over lambda is equal to 1E times 0.100 volt plus 3.90 electron volts. It's an incredibly difficult calculation of 4 electron volts. So that's the energy of the light. The light has 4 electron volts of energy in its photons. Lambda is then 1240 eV nanometers over 4 electron volts. I can do that one in my head. 310 nanometers. Do that with 6.63 10 to the minus 31 joule seconds and try to do it in your head.
Nothing.
Do not work in SI units. It's not the practical thing for modern physics. Now, is that visible? Why not?
It's below 400.
Below 400 nanometers, so it's not visible. This is an ultraviolet. This electrons are really tightly bound. And so shining light on this, if you want to use this, for instance, as an LED detector or something for your DVD player, this isn't going to work. This is the wrong type of metal to use. All right, it's not going to work for that type of thing. Not going to get any current from it. So, and you could use it with UV, but by the way, they're also known to create cancer in cells. Yeah.
We were talking about, this is kind of back from medical, but we talked about the gamma, like for bones.
Yes, this is the same photoelectrons we were talking about.
What kind of work function would a bone have?
Well, we don't tend to think of the work function as in a bone being, because in the case of a bone, you're knocking out the inner shell electrons of the individual atoms.
Yeah.
And in the case of a work function of a metal, and the reason I said metal is the electrons on the outer shell are not held by a single atom. They're kind of going around between all of them, so it's like a sea of gas.
Gotcha.
So that's an average binding.
Okay, all right, that makes sense.
That's the reason we don't do that for bones. And that's why they don't have the same Z dependence like you would expect with bones. But yeah, that's, if you already have this class, then that part of the bone makes it a lot easier. All right, calculate the cutoff wavelength for the metal. So now I'm going to adjust the light, and the question is, okay, so what's the longest wavelength or the smallest frequency that I can, sorry, did it right? No.
Some people 0.
Huh?
Do you be some people 0?
Yeah, so I want to know, as I turn up the frequency, obviously I knock the electrons. There's a minimal frequency or a maximum wavelength at which you'll still get electrons off. So what you do for this one is real simple. If the electron just gets off the metal, it has no energy left to travel. So this is 0. And I'll tell you something else. It's going to be greater than 310. But not a lot, because it almost was stopped before. So it's going to be close to 310. I believe you have to do the calculation for that. That's why I took this off a test. Hey, if it was good enough for a test, it's good enough for doing the class. So, in this case, V stop is 0. And I know that because I'm trying to make 0 kinetic energy. So, E is phi, HC over lambda cut is equal to phi. So, lambda C is HC over phi, 1240 eV nanometers, divided by 3.90 eV, and the electron volts cancel. And you're left with the wavelength in nanometers. And if you do that, I came up with 318 nanometers. So it will never go to the optical range. And you can play with different targets in the FET. You can put sodium and so forth. This is not a good photocathode. If I was trying to make something produce electrons when you shine light, this is not what I want to do. Problem is that the work function is too high. I want to lower that. You can put cesium or other things that like to give up electrons and will lower that thing. So they take filaments and they put them in cesium and they cesiate them in order to reduce their work function to increase the number of electrons they get out, whether they do it by heating them to give them energy, or they do it by shining light on them. And that's why most things will be shiny metals that have had some cesium put on them, or oxide, in order to improve their performance. Last question is a conceptual type question. Describe how the maximum kinetic energy of the photoelectrons is related to, 1, the frequency of the incident light, and 2, the intensity of the light. So let's try 2. How is the energy of the electrons related to the intensity of the light? It's not. Nothing to do with it. The number of electrons, current is related to intensity, the number of balls you throw. But the size of the balls determines the oomph. And that's not related to intensity. Right? It's related to wavelength and frequency. So 2 is independent. Number 1, how's it related to frequency? By the straight line. Because kinetic energy is related to the stopping potential. And we just got through deriving a minute ago here somewhere that we had a straight line for that. I'll put my graph. Yeah. That's proportional to kinetic energy. So it's linear with respect to frequency by a straight line. So it's linear if F is greater or equal to the cutoff frequency. If it's below the cutoff frequency, you don't get no electrons, so you can't really talk about maximum kinetic energy in it. It's a bound. Questions about the photoelectric effect? Simple, easy calculations, no calculus, no Boltzmann distribution, no integrating everything. God forbid you miss this and have to make it up by doing a demonstration of McCoy's method of solving the Gaussian distribution integral. Hopefully not. Next thing about radiation. So, continue with photons. Let's smack things with electrons. And if you smack things with electrons, you could knock some electrons off, and then they could drop down and give off photons. You could slow down, in which case they have to give up their energy some later. By the way, they'll have to give it up by photons. There's all sorts of different ways that you could get it. This leads to X-ray machines. So, sources of electromagnetic radiation. Physics 2, which you should know by now already. Electromagnetic radiation is produced when a charge accelerates. You take a charge. So you sit here with a little electron like this, and that electron goes like that. If you think of those field lines going out from it, in all directions, kind of like this, and I wiggle, those field lines can be thought to wiggle. And that wiggling, that rippling of the field lines, at least the way the 1800 people thought, was the actual wave propagating in space. And we don't think of that same way today, but it's the same thing. That charge, if it wiggles, it accelerates. Then you're going to get electromagnetic radiation. If it's a constant movement, then you're going to get a magnetic field, but it's not going to radiate energy out. Of course, oh, interesting little thing. So the guy's moving along here, and he's a current, so I get a magnetic field. But if I was on the charge, in that frame, it'd be stationary. And there'd be no magnetic field. There must be a connection between electric and magnetic fields. This is where Einstein came up with his ideas of relativity. All right? And that means they're constants, the permittivity and the permeability, epsilon and E, must be related, and they are, through the speed of light. There's only one constant, C. That's what we call an electromagnetic force. They're connected. They have to be connected. Depends on your frame of reference. So for this section, what we're most interested in, nice to always go back and look at relativity, is this is a fact. So if I accelerate a charge, I can produce electromagnetic radiation. This is the whole way that radio, television, and so forth is designed. It also means that you have AC circuits in this room. Those AC circuits, they're going one way, then they turn around and go the other. That's acceleration. That means they will radiate. There's no way to stop that. So the idea that, oh man, power lines are, well, of course power lines radiate. So does your house. All right, let's get to the question of whether it's bad for the cells, not a question of whether it radiates. Of course it does. Can it make a glass tube? Well, sure as hell hope so. We use them in the room. I don't know why people are so shocked by power lines can light up tubes. What do you think these ballasts are doing? Okay. Doesn't surprise me. If you shoot a set of ions or electrons and you smack it into things, when they smack, they're going to accelerate and they're going to slow down and they're going to give up their energy. Now they could do that in 1 photon, 5 photons, 47 photons. But they have to conserve energy. So if they give it in 1 photon, they give all their energy. If they give it in 7 photons, then they'll divide that up and they'll have less energy. That means their photons will have different frequencies. There's a name for this. The German for breaking is Bremsstrahlung. So these are known as Bremsstrahlung X-rays. They are a continuous group because the electron that's shot into a wall, let's say, was not bound. When you bind a differential equation, when you bind a physical system, you quantize. That means you only have certain allowed solutions. Example, a guitar string. If you have a guitar string like, if you bound this end and this end, this is not an allowed wave anymore. That solution is lost. You only get discrete solutions. So when you see something that's discrete, PHYS, for instance, you're probably looking at a bound system. And when you see things that are continuous, you are looking at an unbound system like a free electron smacking into stuff. We'll come back later and talk about, there's a German name for when you bind these things and the solutions that they have. So this is where an electron, for instance, ran into a lead plate. These guys, however, are discrete. They don't come from the same place. When the electron smacks into a metal plate, he may knock off some bound electrons from the atoms of the plate. And those guys, when the other electrons fall down in the bound system, will give discrete peaks. So these peaks are from the target material, and these peaks are from the thing that you smashed into it. These can be used like fingerprints to identify the target. And in fact, we do this. So people say like, hey, this gold ring may have platinum or may not, but we can't tell unless we melt it. Oh, BS. You give me that thing, I'll smack some things in it or shine an X-ray on it, and I will get these characteristic peaks. I'll tell you exactly how much and what you have. We can non-destructively test lots of things.
My uncle actually does that for a living.
Huh?
My uncle does that for a living.
That's cool.
Non-destructive testing for helicopter parts.
Yeah.